Good morning, everyone. How are you doing today?
Good morning.
Morning.
Good morning.
Good morning.
Again,
Good morning.
Good morning. Good to see everyone. A reminder again, if you could, feel free to turn on your camera. It help us to be more focused. All right. So we were talking about using different graph representations to describe motion, right? So different ways for us to communicate information about the motion of an object. So we have already talked about the position time graph, and we can look at the velocity time graph. So just like how we get the slope is a velocity on the position time graph, the slope of a velocity time graph represent the acceleration. So if you're looking at the blue line and the red line right here, the blue line, the motion of the blue line have a bigger slope than the red line, which indicate that the blue line object will have a bigger acceleration. In both of those cases, it is a constant acceleration because you can see that the slope is a constant, right? Meaning that the velocity is increasing, is changing. So there's definitely a acceleration involved, but it is changing in a steady way, right? In equal amount of time, it changes equal amount. So there's a constant acceleration representing first and the second object. But oftentimes it is very confusing for us to figure out what is a positive or what is negative. What does a negative acceleration mean? So I want to use this question as a way to sort of to clear that up. So for example, we are looking at a position time graph. You have a velocity in the straight line sort of going this way from 5 meters per second. So it is asking which statement is correct at t equals 3 seconds right here. Okay, so I've let you guys discuss this for a minute or two, and then once you come back, we can vote on this. All right, just 1 second, and take a screenshot before you leave for the breakout rooms.
Hi, Professor. Sorry, really quick question. My computer audio wasn't working at the beginning of the meeting, so it took me a little while to get it. Has anything like happened so far that we needed to write down or no?
No, we
Okay,
just.
I'm so sorry.
Yeah, no worries.
Thank you.
No problem. As people as people come back, please put in your vote. Okay, let's run for 10 more seconds. With a share. Get the share back. Can you see the share screen or no?
No, we can't.
Okay. I don't know why it's not. No. Let me stop share and do it one more time. Okay. All right, finally. Okay, let's go ahead and take a look at our results. I'm gonna go ahead and end this. All right, so majority of you think the object is speeding up. And how can we tell that it's speeding up? Anybody would like to share the thoughts?
So how I thought of it was that at t equals 3, we know the acceleration is negative because the slope of the velocity at that point is negative.
Okay.
So that means that acceleration is negative. So it has to be A or B.
Okay.
But when you have basically opposite signs between velocity and acceleration,
Okay.
that means that you're slowing down. But if you have the same sign, you're slowing up. So since velocity and acceleration are both less than 0, we know it has to be B.
Oh, very good point. Like you said, here the velocity is also negative and acceleration is negative, so therefore it's going to be speeding up. Very good. I really like the thoughts, and thank you for sharing that. Or in other words, you can look at this directly from the graph. This would be probably 2.5 or something, right? And then at 4 seconds is -5. So the absolute value of this is getting bigger, corresponding to a object speeding up. So I want to use 3 different graphs to summarize all the different situations that you might see for a constant acceleration. Don't worry too much about something is positive or negative. It's only positive or negative because it is in the same or the different direction as the direction you define to be positive or negative. So you have to look at both of the signs of velocity and acceleration to see if it's speeding up or slowing down. So this one is pretty straightforward. The velocity starts at 0, so initially at rest, and it's increasing, right? So acceleration is bigger than 0, meaning that the slope, because the slope is also bigger than 0, meaning that the velocity and acceleration is in such a direction that is in the same direction as you define to be positive. You can define right to be positive, you can define left to be positive. So in this case, it's just increasing. Now this case is also velocity is increasing in magnitude, right? In terms of the absolute value, it's speeding up. But it is in the opposite direction. So acceleration is less than 0. So you have this kind of graph because let's say you want to define to the right is positive, but this object is going into the left side. So therefore you have such a graph. Now this situation is the one we just see in the clicker question. Velocity starts maybe going to the right-hand side, positive, but velocity is dragging it behind, so it's slowing down. Once it reaches a 0 point, that's the critical point where it's going to reverse directions, right? So it slow down and then come back. Come back is speeding up in the other directions. So remember, knowing if your acceleration is positive or negative doesn't really tell you if it is slowing up or slowing down or speeding up. So you need to see if the acceleration and velocity are pointing in the same direction or opposite directions. So don't put too much emphasis on the signs of these quantities, because the signs is determined by which way you define to be positive. Let's look at another question. This is a bridge question you have answered. So from a position time graph, we can get velocity. From velocity time graph, we can get an acceleration graph. So let's see these VT graph and XT graph is given. We have to choose the correct graph for acceleration over time. So which one of these do you think is correct? And how do we know? Anybody like to talk about
Are our only answer choices A and B?
Yeah, these are two choices.
I think it's A.
Okay.
Because like the same logic I had last time with the integral. I mean, sorry, the derivative of a parabola is going to be a line. So B is not a line, it's an absolute value function.
Okay, so you're looking at a velocity time graph and look at the slope of this, which tell you information about the acceleration, right? Yeah, very good. So if we were to look at the slope of this on the left-hand side, I have a negative slope, right? So that means a negative acceleration, meaning that the acceleration is in a opposite direction as what the question have defined to be positive. So you should draw a acceleration that is less than 0, and only A is correct because you can see this is less than 0 and this is bigger than 0, so that section is wrong. Very good. So we choose A. All right, you can change back and forth between different graphs. Given one, we will be able to tell what the other one looks like. So one final sort of a summary of all the possible graphs we might see. For a constant velocity, meaning that the velocity does not change. So constant meaning that it does not change with time. So if you draw a VT graph, obviously it doesn't change, it should remain flat, right? A flat line. Now, for if velocity is constant, do you have any acceleration? No, right? If there's no acceleration, so therefore velocity doesn't change. So acceleration will be 0. So if you draw the acceleration time graph, it's going to be 0, a flat line on the 0. Now for position, then you will just change your position in a linear way, right? Giving you a constant slope. The other type of motion that we deal with a lot in this class is constant acceleration. So acceleration is a constant. You can see that acceleration is a flat line, doesn't change with respect to time. But that shows your velocity would have a steady slope. So velocity would be a straight line going up, right? And in this case, your position would have be changed in the parabolic motion. So sort of looks like a parabola on the graph when you draw it. So these are possible graphs you might encounter in this class. So here we already talked about, okay, this will kind of look like a curve, but we haven't really derived this using in the formula way. So here, next, I want to be able to derive the exact kinematics equations that we will use over and over again to solve all the problems in this chapter. Like I said, we start with the two fundamental definitions. I have put a box around these equations earlier. I hope you still remember that the definition of velocity is dx over dt, the derivative of position over time. The definition for acceleration is dv over dt, the derivative of velocity over time, right? So we will start with these two fundamental definitions and derive the kinematic quantities equations we're going to use to solve problems. So you will see my derivation, you understand this, but once you start solving your problem, you do not need to do the derivation again. It's derived and you can use the result right away. So let me start with the first one. V is dx dt. So I want to be able to derive the function for position change with respect to time. In fact, I find it a little bit easier to start with the acceleration first, because I realize the velocity is also changing with respect to time. But when I deal with a constant acceleration, the acceleration doesn't change. So it's easier to start with this equation first. So I'm going to start here. Multiply both sides by dt, you get dv is equal to a dt. And then integrate both sides. This becomes velocity as a function of time, right? This is what we want to solve for. And a is a constant, which means you can take it out of your integral. And what would you get? You should get a constant plus a times t, right? So you get this equation. So why do I add a constant? Because you know when you take your derivative, right? You take the derivative of both sides, the constant will go away and t becomes dt. So a dt and constant will go away. So any kind of constant could satisfy this equation, could still work. That's why I need to add a constant here. So how do I define the constant? Like solving all differential equations, I would use some initial conditions. In this case, our initial conditions are decided by the physics, what type of physics we're talking about. So you would say, okay, what if at t equals 0 seconds, my velocity at t equals 0 is some initial velocity. So this is only, all of this is telling you at the beginning where you decide to look at the initial moment that you choose to evaluate the motion, the object is moving with some kind of velocity. We call it the initial velocity, whatever it start out with. So we call it V naught, V0, V subscript 0, V naught. So if you plug this into your equation, at t equals 0, a times 0 is just 0, right? 0 plus constant should give you the velocity at that moment, which is 0. So this constant should just be V0, V naught. So you have derived your first kinematics equations. Is velocity at any given moment is your initial velocity plus at plus acceleration times time. So here I wanted to pause and ask two questions. First is, you can see how given an equation, I try to say it out with words. I translate the equation into words that helps you understand what it means. So I'd encourage you to do the same. So is there any questions on the meaning of this equation? This equation means the velocity at any given time is equal to your initial velocity plus your acceleration times the total time that passed. So does that make sense?
So we're the second main line on the page, does that say v of t equals constant plus, and then is that a times t or a v t?
A times t here.
Yeah. Oh, okay. So that's a times t.
Yes.
Okay, thank you.
Times t. Thank you. So we all understand the meaning of this equation? Any questions? Okay, so I'll repeat the meaning of this question, this equation. This equation is telling us the velocity at any given moment of this object is equal to your initial velocity of the object plus the acceleration of the object times the total time that passed. Make sense? All right. So another question is, any question regarding the derivation, how I derived the equation? If not, let's derive the second kinematics equation. I wanted to be able to find a formula for the position. And I will use this. So dx is equal to, v is equal to dx dt. So that means dx is equal to v times dt. Now v has already have a function. So I'm going to use this function and plug it in. V, so this is a generic v at any time, which is v naught plus at dt, right? So I'm going to integrate both sides. This just gives me x, right? And here I will do one at a time, v naught dt integral and at dt integral. Okay, and I should also have a constant. Don't forget to add a constant, because when you take the derivative of a constant, it goes away. So you can add a 2 here, 5 here, you can add 100 here. It could still satisfy your original result. So your solution needs to be general. Okay, so what does this one become? This one becomes v naught is a constant. So integration of v naught dt becomes what? Anybody can finish my sentence?
V naught times t.
V naught times t, excellent. And this one becomes? Acceleration is a constant. So
I believe it would be a over 2
t squared.
a times t squared over 2. Excellent, thank you so much. And a constant. Very good. You can always take a derivative going back to see if that worked out. You need to confirm and double check it. So this is your final equation. And again, we don't have this constant, right? So again, we'll use our initial condition. At t equals 0, your position would be at some initial position that the problem have already given you. So we call it x naught. So you can see that if you plug in t equals 0, this term is 0, this term is 0. And for this equation to match up with your initial conditions, you need the constant to be simply x naught, right? So your final, another kinematics equations is x naught plus v naught t plus 1/2 at squared. So anybody could, again, look at this equation and say it out with words, the meaning of this equation, just like how we did it with the velocity. Anybody could try that?
At any point in time,
right?
Your position is going to be based on where you started, plus how fast you were going at it at the beginning. And then, but then that's also dependent on how long it's been since you were going.
Okay.
And then it's based on how fast, or how the magnitude of how your speed is changing. Do we have to like deal with the constants right now, or can we just be general like that?
That's very good. I like that how you described it. It does depend on where you start, does depend on your initial velocity, also depend on your rate of change of your velocities, which is your acceleration. That's very good. That's how you make sense of this equation, right? If you wanted to simply add the constants, you would say your position of any given moment is equal to your initial position plus your initial velocity times time plus 1/2 times your acceleration time squared. So that's just how you will read it out in words. All right, so we have derived these two equations. When your initial time is not necessarily 0, we just add a delta t, meaning that's the total time that passed by from the initial point. But you can write t here, or you can write delta t here. It's up to you. So if you write t here, meaning that implicitly you have set your initial time to be 0. But if your initial time is 3 seconds and then you're looking at 5 seconds, obviously only 2 seconds has passed by. So that's why we added a delta t here to show it's the total time that passed by from the initial point. These two equations are, a third equation is not new. This is not a new equation. This is not new information. It can be derived from equation 1 and 2 combined. This one, get rid of the time. You can see it does not have timing here. So when the question give you some quantities, let's say the question give you velocities, give you displacement, and want you to find acceleration, you will find this equation is easier to do because you can get around finding the time first. So really depending on what the problem asks you, you can choose to use any of these equations. But these two are the ones we just derived. And this one is sort of a merge of the other two. It's not new. And don't worry too much about memorizing them. But once you get really familiar, you probably will, these will become memorized, but you can always have this on your sort of equation card, and when you need to, you can refer to them. The important thing is for you to understand the meaning of those equations, not to memorize them. So you can see constant acceleration is where A is a constant. So constant velocity is really only a special case for constant acceleration. Why? A special case where A is 0, right? That is also a constant, which means for equations that you use for constant velocity, there's no need to derive it. You can take these two equations we just derived and substitute your acceleration to be 0, right? Because if you have no acceleration, obviously velocity will not change. So you put A equals 0, V equals V naught, well, duh, because velocity doesn't change. So velocity at any given moment is always your initial velocity, remain that same constant and doesn't change. Your position will simply be also something very intuitive, is where you started and how much extra you have gone by as time goes on, is your initial position plus your initial velocity times the total time, right? If you start out 100 miles from home and you drove 50 miles per hour for 2 hours, you will end up with 200 miles away from home. So that's some common sense. So again, there's no need to memorize these equations. You can probably write it out just based on your understanding of what the motion should be. So next, we are actually going to use these two equations, the constant acceleration, these two equations, to help us solve a problem. So this is a very, one very common type of problem in kinematics is catching, one object catching up to another, right? The train catch up to you, or two cars catching up to each other, catching and passing each other. So that's very, very common. This one is slightly complicated, and I think it's a very good question because it helps us practice a lot of these equations we did. So what we are going to do is we actually will break this question down into multiple steps, and we'll do it one at a time. Eventually, we will be able to solve this problem. So this clicker question sort of just present what the situation to you, and we can read this problem together. You have a truck traveling at this speed, is approaching a car, and the car at the moment is stopped at a red light. So it's approaching the car from behind, right? And when the truck is 100 meters from the car, the light turns green. So at that moment, the car immediately accelerates and keeps going forward. And the acceleration is 2 meters per second square. But the car cannot continue to speed up forever. So it will reach to a maximum speed and then kind of just remain that same speed, a constant velocity for the rest of the travel. And we are assuming there's no more red light in front of the car with the situation we are evaluating. So simply the truck is here going at a steady speed. The car stopped here. And that moment, car start accelerating. And once it reaches maximum speed, it will go with a constant velocity and the truck will continue to try to catch up with the car. So we're trying to find which graph represents this situation. Describe the motion of the car of these two vehicles. You can see that to be able to find out which is correct is not that easy. You can see these graphs all look kind of similar, but they're all a little bit different. So which one is correct? We have to answer some follow-up questions to be able to select the correct graph. But for now, do you have any intuition? So I will just go ahead and start this poll. You don't have to think too hard, just basically, okay, intuitively, what do you think it will roughly look like? And then we will look at the follow-up questions. Okay, any other more predictions? It doesn't have to be well thought. It just could just be intuitively which one best match up with your thought. All right, let's run it for 10 more seconds. All right, I'm gonna go ahead and end this, okay? All right, so here is our predictions. We are kind of all over the place, maybe slightly more vote toward B or C, and equally split between A and D. To understand which graph it might be, or you may not be able to narrow it down to one choice, but perhaps we can narrow it down to a couple choices, given the information given the information that we already have here. So now let's look at the meaning of these graphs, okay? Let's look at the point graph A. So you can see that for graph A, the car start out at a time equals 0, position at x equals 0, okay? And you can notice that at time equals 0, where is the truck? What does A represent? The position of the truck is it intersects with a value that is on the positive x-axis, right? So what does A tell you? A tells you that at t equals 0, the truck is what? Before the car or behind the car?
In front of the car.
In front of the car, right? So, but then we're saying it's approaching the car from behind. So, so that's not the information we want to represent. So you can see the one that shows that truck is behind the car is B and D, where the truck is behind the car. Now C shows truck and car are in the same position at t equals 0 because they overlap. You can see that at t equals 0, both of them have a position at x equals 0. So meaning that at that moment, they're exactly starting out the same place, but they did not start out the same place, right? One is at the red light, one is behind the car. So you can probably narrow it down to B and D. And the difference between B and D is, so I'll ask you guys, what do you think the difference between choice B and D is? The main difference.
car and the truck being at the exact same place at the same time?
Oh, the truck, at some point, the truck and the car are at the same time at the same location. Yeah, very good. They meet at the same spot. So D represents there is a moment in time where the truck catch up with the car. But B says the truck will never catch up with the car, right? That's the main difference between these two graphs. So which one is it? That's what I mean by we cannot, with the information given, we need to do some calculations before we can answer that question.
You know, like that light gray line on B,
I'm sorry?
like, you know, on B where it says car,
Yes.
that like to the right, the line just kind of becomes a little lighter gray.
Yes, yes.
That's supposed to represent when the car has its final speed of 100 kilometers per hour.
Right. It represents it's not that parabolic curve.
So then wouldn't it be D? Wouldn't it be B because D never shows that, and we know at some point the car has to have that?
Could be, although people who draw D is saying, well, maybe that happened at that takes about 2 minutes. I'm only drawing whatever happens at a minute and a half.
Oh, okay.
So that's also okay. But that's a really good observation. We do want our graph to be as thorough and rigorous as possible. So now, before we can answer that question, let's look at some follow-up. These are follow-ups. After we answer these follow-ups, we can go back and answer the original question. So the follow-ups are small questions that's breaking it down in many small steps, and that's each of them is simple to answer. So the first question, how long does it take for the car to reach its maximum speed? That tells us at what point should we start looking using different kinematics equation to analyze the car? So we need to figure out, okay, from what time, from 0 time to which second, we need to use a different method. All right, so I'll give you guys maybe a minute and a half in your breakout rooms to look at this question. And whenever you come back, you can vote. And make sure you record the information before you go, okay? Right, so as people come back, please put in your vote for this question. All right. So one thing I wanted to talk about is for solving problems, there's some general good strategies or steps to follow. First question, we have already talked about what this question looks like. So while you're talking it over, you might want to draw a picture to help you visualize the situation. And you can label your quantities. So for example, I draw my car here, my truck here, and my positive is to this positive direction. So I can label the quantities that is given. So the truck is traveling with this speed. So I'm going to say the velocity of the truck is 14 meters per second as it's given. And the truck is 100 meters away from the car. So here I'm going to say the position of the truck. This is the distance here is 100 meters. So where you put your initial, where would you put your origin is totally up to you. You can put it here or you can put it here. So if we put it here, say the initial position of the car is 0, then the initial position of the truck would be negative 100. Okay, so you can see that. Draw a picture, choose a coordinates, and label your quantities. And one other information that is given is the car starts at accelerate at 2 meters per second when it reaches a maximum speed of 100 kilometers per hour, which is 28 meters per second if you do the conversion. Okay, so those are the pictures. And then next, we wanted to be able to choose whichever physics we want to use. So what we mean by choose the physics, we mean that what kind of motion the object is having. So you can choose the relevant quantities, right? So the question is asking about the car. So choose the physics for the car. What kind of motion the car has? Is it a constant acceleration or is it constant velocity? What do you think?
Constant acceleration?
Yes, before it reaches maximum speed, it is a constant acceleration. So the constant acceleration has these two equations we just derived. Okay, so once you figure out the physics, you can choose equations to use. Which equation do you want to choose? Which one is more relevant to answer this question?
The equation for velocity?
Yes, very good, because it's asking about the time and it's telling us about the maximum speed, how much time we reach the maximum speed. So we would choose this equation. All right, so maximum speed is 100 kilometers per hour, and we know that's 28 meters per second. Initial velocity is what? What is your initial velocity of the car?
14.
Initial meaning that at this moment, the car start, when it was a red light, the car stops, right? When it's green light, the car go. So initial,
it's 0.
It's 0, very good. So all of those information we interpreted from the problem, 0. And acceleration is given 2 meters per second. And how much time it will take? This is what we want to solve for. You can see that you can solve for the total time is what? 28 divided by 2, 14 seconds, right? So 14 seconds is the correct one, right? Okay, And you guys did a good job. I think the majority of the correct answer is correct. The choice is correct. All right, so with that, you can see that is the car. And that still doesn't tell us if they pass or not. Now we need to answer two more questions is during this time, how far did the car travel? Okay. And then after this question, we answer during this time, how far did the truck travel? The reason for answering this question is okay, within that time, did the truck ever get past the car? Because once the car reaches the maximum speed, you can see is twice the speed of the truck. If at that moment the truck hasn't passed the car yet, there's no point of it, no way for it to pass it ever beyond this time. So that's why we're trying to evaluate what happens within this time. And we need to answer this question and the follow-up question, how far does the truck travel during this time? We're out of time right now, so we will do this on Monday just to finish answering these two questions. Or if you like, you feel free to do this on your own if you want. But I will end the class now, and I'll see you guys next Monday.
Hey, Professor, I have a question.
Yeah, go ahead.
On like the achieve the web assignment or yeah, I was kind of stuck on the first homework with the order of magnitude. How do you find that? I was never able to. I finished everything else except getting that one.
Okay. The first question on the homework, right?
Yeah, it was like something about order of magnitude. I didn't know how to do it.
Okay. It may be just the language. I do have to go now, but I will take a look at that question and I'll send you an email. And
Okay.
Could you please tell me your name so I could make sure to send it to you?
Brian Nguyen.
Okay, 1 second. Okay. Okay, I will get back to you on that.
All right, thank you so much.
No problem.
Next class, Professor, I had a question about one of the kinematics equations, the ones that we didn't derive. Could we go over that next class then, since you have to go now?
This one, right? You mean the v squared minus v naught squared, that one?
Yeah, because that to me, that one has a lot of similarities to the equation of a line. And I wanted to know if I was right about that.
This one?
Yeah, because you know how a line goes like y minus y sub 1 equals m, which is in this case 2a times x minus x sub 0. I don't know, it just reminded me a lot of the equation of a line.
Oh, of a line? You mean you want to use this to solve the car truck problem?
No, just in general, I had a question about it, how it was derived, because to me it has a lot of similarities to the equation of a line, except that the v's are squared in this case. But other than that, it reminded me about it a lot.
Oh, sure. I could certainly talk about the derivation, but maybe not in class. I could post a derivation online.
Okay.
Because doing this is tedious. It's really okay. Solve t in terms of v and a and plug it into these two.
Okay.
Yeah, it's just that. It's just the algebraic. It's pure math.
Cool. Thank you.
No problem.
Have a good weekend. See you later.
See you. Bye.
Professor, I have a real quick question. The graph with the car truck, the parabola, and the line.
Yeah.
I think Juan mentioned that light gray thing.
Yeah, light gray. Yeah, it's.
So this is the first time that I've heard of this case. So is this for all cases where there's a light gray?
No, this was not a break point of choosing B and D. If it's an exam, it will be much more obvious. Be something like that. It's not. It will be more obvious.
Okay, so
that's.
So this was just the printout then.
Yeah, it's. I did draw these graphs. So while drawing it, that wasn't my concern, but I do think about, okay, what I've wanted to show, it's maybe not a parabola all over, but I didn't, that's what not really my concern. So I just wanted to show these two differences. Don't worry too much about that. it would not
Okay.
be that you need to be tested on.
Okay.
Yeah,
All right. Thank you.
no problem. Bye-bye.
Bye.